Welcome to the second day of our annual technical review. So why don't we briefly summarize what happened yesterday and put that in the context of what today. Walking through the cycle processing thing, and we were focusing yesterday on methods that derive from Green's theory, either for wave-field separation or for wave-field prediction. And for wave-field separation, the procedures are for a reference wave separation from reflection data and for deghosting. And we said that we think there's a lost opportunity right now for the methods that we devised for separating reflection data from reference waves in the marine setting. We have the acquisition, and we ought to be predicting the reflection data and all offsets in our data, not trunking the reference waves, which you can predict it with the new kind of field and derivative measurements. The field and derivative measurements have excited the people for broadband. They want the low frequency, and that has generated an interest in ghost removal, obviously, for the notch at zero to reduce the low frequency for FWI and other purposes. And that's we're very happy with that use. One, as we mentioned yesterday, if you had to say what is M-OSRP providing in the area of ghost removal, is the ability to remove ghosts with a measurement surface and not necessarily autonomous. So you don't perform a Fourier transform laterally, you just get the surface and you do an integral on that surface. So that's a differential value. We think that this, we need to encourage this more by showing examples of field data of what happens when you measure all the elements. You don't have to subtract and cut that reference wave. Yes, injure your long offset data. It's totally unnecessary to do. With the current acquisition, it's just changing the Green's function in the same interval that does this, does that. And that's been delivered into the 3D. We need to show some examples of that on marine field data, difference in observable reflection data, low offsets. So that was, yesterday you saw two talks by Jing Wu on this kind of wave separation application from Green's theorem for onshore application. And as you'll see today, that's a critical component of our strategy for doing more effective and needed capability for multiple removal, both marine and onshore. And onshore, it's a tough. This is tougher. This is all tougher because the near surface can be difficult, can be the most difficult thing that people onshore deal with at times. It's complex. They have crusted sediments and all kinds of complexity. And Jing Wu mentioned that we have a method that can indirectly back out near surface properties using an invariance. In other words, there's a wave field prediction that says you get the reference wave. Well, the reference wave is a wavelet, let's say, times the Green's function. Whatever that reference medium is. The question is, let's say you don't have to write Green's function because you don't have to write near surface. Then when you evaluate that reference wave at different points, you'll get a different wavelet. And the wavelet is not the wavelet in the Earth. The wavelet is a source signature, and that should be invariant to the output point. If it isn't, you got the wrong reference. So that's an indirect procedure. We showed examples. We're also looking at how to do this activity, this wave separation onshore, without needing information of the near surface, and below the measurement, above the measurement, and at the measurement. That's something I'll pursue. The other application of Green's theorem was for reminding us that John Claerbout had three imaging conditions. And in some way, it's, when Stolt and I were looking at that kind of thing 25 years ago, it was clear that his third edition was the most capable, the most definitive, the most flexible to actually determine structure, whether you had specular or non-specular, and for doing amplitude analysis. You could simulate what a plane wave would do at the depth point if you experiment there. Somehow, and that, by the way, enters all the people here who are doing inverse scattering, internal multiple attenuation, are using Claerbout imaging 3, the thing we call B1, so water speed uncollapsed migration. So that's sitting in, we couldn't imagine anything else. We were so taken with that in terms of its benefits. With the RTM and other activity, somehow Claerbout 2 became all the vogue and is the vogue today. So what we are saying is that what we have provided is the math physics and for how to predict Claerbout, the experiment corresponding to Claerbout 3 imaging, which is predict the source and receiver in the Earth. What would it do? First of all, in Claerbout 3 is very different than Claerbout 2. Claerbout 3, there's only one wave field. You have what you measure, and you're predicting that wave field. You understand? There's no two wave fields. It's what would the source and receiver predict then? A field. Understand? Whatever that measurement is. It starts with actual and predict. In Claerbout 2, it's a very reasonable, and we'll say some further words. Claerbout's idea in Claerbout 2 was, if you have a wave that comes down, and then it reflects and goes, there's a reflection that leaves the reflector, there's a moment in time when that down wave and that up wave are at the same place in space and time. Yes? And that, at that time and that place when they're coincident is the location of the reflector. Yes, that's entirely reasonable. Yes. So we'll see what, there was a discussion that will make a comment in terms of our view, in terms of primaries and multiples. But what you will get this year is how to arrange Claerbout 3 in a medium which is heterogeneous. How do you numerically generate a Green's function that will predict that experiment where you have a lateral varying medium? How do you predict it under it? That's a numerical thing. And Professor Fong Lu is in the middle of that, and there is an ongoing calculation. As soon as that calculation arrives, we're going to send that to the sponsors. Because if you come with some velocity, x, y, z varying velocity, how are you going to realize a Green's function in that medium such that it, with its normal derivative, both vanish at some level? Yes? We have to show you what are the numerical issues there. Yes? So some guide. Understood? That's going to be a delivery before the next meeting, but that calculation is ongoing at the moment. Understood? Yes. So then you can have your own velocity model, yes, and we'd be happy to work with you on how to arrange that kind of experiment to occur. We said that definitiveness was very useful in Claerbout 3 because let's say you took primaries and multiples and you took the data on the surface and you predicted what Claerbout 3 told you to do at depth, and you asked for time equals 0, what's the role that multiples of free surface and internal play in that imaging? And we showed analytically and with some kind of cartoons that if you have an accurate discontinuous medium, then the experiment with primaries and every variety of multiple will contribute to what the experiment is at every depth. Or they will have their own primaries and multiples at every depth, yes? In other words, that whatever source and receiver is there. But once you make them coincident at time equals 0, that only the recorded primaries contribute if you have an accurate discontinuous medium given, yes? That was shown and published. We published that in the Journal of Seismic Exploration, Professor Fangdu and myself. So that, yes, if you have a smooth medium and you do Claerbout imaging 3, predictor experiment, like stalk migration, then every event in your data will be located, every event, primary, free surface, and internal multiple will be located where water speed sends it. Yes. So every single multiple, if you have a smooth velocity, will be a false image. So that's what Claerbout 3 says. So there was a bit of, then we said, okay, that's great. That means multiples, if you have an accurate discontinuous medium, and you take the most capable imaging principle that we know of, which is Claerbout imaging 3. If you have an accurate discontinuous medium, there's no need to remove multiples. They cause no harm. Understood? They don't affect the image. They only will give you a problem if you have a smooth. Understood? That's very important. So the whole reason for removing multiples is our inability to get an accurate enough velocity. Understood? If we had accurate enough, the multiples would not cause a false image. They cause no contribution to the imaging. So if we ever could get velocity analysis accurate enough, you wouldn't need to remove multiples. Okay? Well, it's sort of circular because the methods to define velocity, tomography, common image scatter flatness, FWI, and so on, in general, assume that you only have primaries. So, you understand? It's circular. So that's the state of things. So then we said, okay, so that's a wonderful theory. It says if you have primaries, that's all you need for the most accurate form of imaging. And then we entered the subject, well, what are people doing who are saying, and they are deriving benefit from multiples. So that is an issue that only arises as an opportunity if your collection of primaries is inadequate. If your collection of primaries is adequate, that's the end of the story. Okay? All you need is primaries and a wave equation migration. If the issue of making use of multiples is to supplement the primaries that we measure. Yes? To give, not to supplement the primaries themselves, but to supplement the images. Yes? To get an approximate image of unrecorded primaries. That's the reason. So I just, there was a bit of a discussion yesterday about whether that's migrating multiples or migrating the unrecorded primary. So Dan won't be here today, he's called away, but that was a very important discussion. And I'd like to, we already know from Claerbout 3 what happens when you migrate multiples. You understand? They either don't count or they cause a trouble when they're treated as an event. When you treat them as an event. So what people are doing, and to make use of them, and Chow Ma showed a convincing example, and we have field data examples, is they're this is the agenda. But here's this idea, which is a form, a realization of that idea for Claerbout imaging 2. In other words, if this wave goes down, and then there's a wave that goes up, and where the reflector resides is when the down wave and the up wave are at the same point in space and time. In other words, they could be at the same point in space, one delta t down, one delta t down from the, they're at the same space, but not at the same time. One is at delta t, one is at final t minus delta t. Yes? It's when they're at the same time in the same space. So there are different ways to realize that. you would imagine convolution would play a role, shifting, and this is certainly a realization that we've adopted. And if you apply it, all this is doing here is, so let's understand, what Claerbout 2 says to do with the receiver is exactly what Claerbout 3 says to do. What would the receiver have done? What would the receiver have recorded? Understand? That back propagation is identical in 2 and 3. It's on the source side that they differ. On the source side, it says, produce the field that the source will, the direct wave that the source brings, yes? Claerbout 3 says not to do that. It says predict what the source will be at depth, yes? That's the difference right there on the source side, yes? To make the experiment. Here, the receiver is being predicted, but the source is just, you just send that wave, rather than say, what would the source and receiver do? That's 3. Understood? So on the receiver side, they're identical in concept. And so the point is, as Chow showed, with this kind of implementation, with that integral of that thought, you will move this down wave and down, and this up wave back until they're at the same time, at the same position, and you will locate and get, in fact, an estimate in normal incidence, an estimate of the normal incidence reflection coefficient. Not an estimate, you'll get the normal incidence reflection coefficient. And there that is. Now here's where it's important for us to understand. You have this multiple, yes? You have this multiple, and the multiple is measured and it's deghosted on both sides. There's an event here that's a measured primary, which has been source deghosted, where you kept the receiver ghost and you didn't take the unghosted part. So it's only down at the receiver, the opposite of being deghosted, yes? So this is, and then this is then seen as a wave that's going down, and this wave that's going up, then make this go down, make this go back, and see where they're coincident, yes? Understood? That same kind of thinking as for a primary. But if you look at this kind of example, that when you take this event and you take it back, the velocity that you use is the velocity of this. This guy here could have been running all around. All you care about is this being down. And I can change this set of velocities here in a complicated form here. The only velocity that you're looking at input into that machine is the velocity of the unrecorded primary. Yes. So if you imagine somehow you are imaging a multiple, as we showed, you have to have that the median that the multiple went through. Yes. Which could have been deeper. Yes. You don't need that. So you are not taking this event and imaging it or migrating it, and it's a misnomer to say it. You're not doing that. If all I need is the velocity of this, the unrecorded, it's clear that this is going down, this is going back, and you're locating that approximately where that primary would produce an image. So that's why I make a statement, multiples can be useful, but they're producing an approximate image of a primary. So you say, why are you carrying on the semantics? Because you're at a university? No, well, it matters. It matters because we see other words. We see data-driven. Data-driven used to mean the algorithm cared about data, but not surface information. That's the second part is what it meant. Well, now it means, did you use data? Okay, it's data-driven to find the velocity. Everything's data-driven, okay? Now we have direct methods. There's a method, some talk given in a workshop on at the upcoming SEG, It's a direct method to do modeling. It's direct, indirect. I came to work, I didn't stop at Starbucks, I directly modeled, so it's a direct method. You understand, these words start wandering away from their meaning and become meaningless is the point. The idea of migrating a multiple, okay, other than through that discontinuous where you have bringing it down, in this sense, you're not doing that. Okay? Because I could have this guy with many, many velocities. The only thing that I need to get that approximate image is the unrecorded parameters information. For me, that settles it. Okay, is everyone going to agree with what I said? No? This is being recorded. Yes. It will be on our website within 2 weeks. It's where I stand on the subject. Okay. By the way, for those who, these are Chimingwis, have been very useful. As he come on Costa, we had a lunch a few months ago where I told Nizar, who's an expert at this, very enthused about using multiples, but very clear about what it is and isn't. And I said, I have a hard time getting a theory from some Green's theorem or something. And he said, well, because there is none. It's ad hoc. It doesn't mean it's useless, you understand? It's sort of, look, you see this works, yes? And that's why when they have the crosstalk, as Richard Coates says, it's hard to find a systematic way to get out the crosstalk because we don't know the method, how it would be formulated without the crosstalk. Yes. Again, that doesn't mean it's useless. Do we think it's useful? Yes. Do we plan to use it? Definitely. Yes. We're just trying to define what it is and what it isn't. Okay? So, Imtiaz Ahmed from BP said that he thought, I thought I had made enough statement about industry usage. He thought it would be important, I don't know exactly why, to make it clearer. I guess there are people that he knows who feel that the only data that what we deliver for multiples works on M-OSRP synthetics. It's a strange comment, but he told me you should show a list of so that's what this is. Okay, understood? It's a little embarrassing to go through that level of detail, but the sampling, these are the companies. So if you see him test, tell him please I did what he asked. Okay? These are the companies that are providing services. Malcolm Griffith here, PGS and Schlumberger. And these are the companies that have published papers that refer to this method in terms of their usage. And now everyone can say they've seen a list of papers. Okay. Papers, oil company papers, all with ISS multiple, okay? And then there are quotes from Petrobras, from CGG, from ELO, talking about the standalone capability for one reason. The only reason it's standalone is it doesn't require subsurface information. And it's the only method that doesn't. So that's that. Okay, so there's a SEG workshop I mentioned that Joppa they organized, and I don't know, some 9 out of 10 presenters were talking about that method. Okay. So I think we're done with this.